Hello students, in this video we'll discuss about universal Turing machine and undecidable problems. So in the last video we have discussed what are the languages accepted by the Turing machine and when we can call it as a recursive and when we can call it as a recursive enumerable and how to convert an halting to acceptance, all those. Then first we'll come to this. What does it mean by a standard Turing machine, how it is going to work, right? And what is the need of this universal Turing machine? See, let me give you the scenario here. See, assume that if you are asked to construct a Turing machine with some states, then you'll be having a tape here. At the end of the tape is denoted with the blank symbols, delta. And you're having like 0, 1, 0, 1. Something we are performing some complement or something like that. And we'll be having a head, read-write head, which moves in bidirectional. And for the complement, how many states you want, whether it is 2's complement, 3 states are enough. So like Q0, which is going to change 1 to 0, Q1 left side, and Q2 accept and something. Okay, so first it will point into the starting state and it moves based on the input symbols, then left right movements changing the state, everything will be taken care by here. So this is a Turing machine for performing some complement. Okay, assume that 1's complement or 2's complement, whatever it is, right? Then once this Turing machine is done, then how to process the strings, we have to run an algorithm, right? And so that if the input is given to this Turing machine, and it will write a separate program to perform this acceptance or processing the input string. So like you have to mention that if it is 0 where we have to go, if it is 1 where we have to go, everything you have to write the code, you have to represent it in a program. Assume that we have another Turing machine which is going to accept the language of a power n, b power m, c power n. Then again you have to take a tape, separate tape for it. Okay, then you are going to have something like a b b c c, right? And we are having a head. Then again you have to write the transitions like with the 5 states or something. And for this, if you are given a string, how to accept it, again you have to write a separate program for this also. So here we have to write a separate design for it, and here also you have to take a separate design or program to accept the strings. So like for everything you have to go with that. Let me take an example. Assume that you are constructing a house, right? Home. So then we may need some percentage of cement and percentage of sand, water, right? So for to construct the based on the ratio of this, you have to mix it, right? The concrete or whatever it is, right? You have to go with that concrete mixer. You have to the person, the labor will do individually. For example, someone who is constructing a hospital or some commercial building, right? Apartment, we can say that. So we use the same things, but in a different ratio. Like we can go with cement and sand and water. You'll do it in some other way. For example, if the home you are constructing in your home, you will may increase some cement or you may go with the sand instead of robo dust. Okay, that's your wish, right? So for this individually, you have to contact an engineer and you have to ask what we have to do, and individually we have to do for this everything. We have to do it individually. Then we'll be having some concrete mixers, right? So if you tell that, okay, you have to give an input like I'm constructing a home and I'm a builder, right? Then what you'll do based on these inputs, the concrete mixer will do the mixing of the cement. They'll know how to deal with the builders. For example, if you do it, so I'm constructing a home and I'm a owner of that. Then okay, well and good, you are the owner. Then it'll on the same. We use the same concrete mixer, but based on the input, it works. You don't need to go and contact individually engineer or someone to you. Okay, what I have to do for this situation? What I have to do for this situation? You don't need to do such, right? So here, if there is no such a mixer, right, what will be happened here? You have to do it everything in your own. For individual, you have to run a particular scenario. As you are having a generalized mixer here, if you give some input, then based on the input, whatever you are doing, it is already having some mechanism to do it, and it will do and will directly come to your place wherever you are constructing a home or build. So based on the inputs, it will do its process. This is called the generalized mission. And we are having some disadvantages here also. Sometimes we don't require, right, like the quantity, whatever the quantity is provided, we don't require it. So for a small house, if you are constructing for a big apartment, that has to be roam more number of times. There are some disadvantages of it. So same way here, if you want to construct a Turing machine for every situation, your wish, or you can build a universal Turing machines. In earlier situation, for different problems, you have to take the different Turing machines, right? But here we will be having a single algorithm for all the problems. That is called universal Turing machine. So it is an ordinary Turing machine which calculates the machine for each and every problem individually for all the input strings. Okay, so what you have to do here, first you have to give the description of special machine what you are constructing, right? The Turing machine for which problem here, like home or apartment, that you have to tell, and what are your specifications you have to tell. Just by giving those two, just hand over it to the universal Turing machine, and it will respond with your machine like home or apartment, whatever we have, and the specifications what you have mentioned, then it will give you. That's it. So that is called universal Turing machine. Then what we have to do here, these universal Turing machines are having three types. One is description of your machine for which you are going to construct. Like if it is 2's complement, give the description of what is 2's complement. If it is 0, what we have to do. If it is 1, what we have to do. Like you'd give the description of it. Okay, and what is the input you are giving to it, that you have to specify in the encoding of mtype, right? The input what we are giving. Then in the third one, what are the states, and always it is going to point to the current state. So simply you don't need to do anything here, just give the description and the input and the states, and always it points to the current state. Then if you run this machine, it will tell you for your appropriate machine and the input string what is the output we are getting, that will give you, right? So for all the problems where we have to do, what we have to move, which state we changing, or everything you need to do it. Okay, so that's about it. And what are the necessary conditions for constructing the universal Turing machine? The input alphabet of Turing machine standardized must not contain the symbols absent from the input alphabet of universal Turing machine. Here U is universal, means whatever the alphabet defined by the universal Turing machine. For example, if it is A comma B comma C or 0 comma 1. So if your Turing machine contains other than these symbols, you cannot give it. You have to change the symbols. In same way, output alphabet of the Turing machine also must be the subset of the universal Turing machine. So we can build a standard Turing machine, universal Turing machine for a standard Turing machine with a fixed alphabet, which is also the alphabet of universal Turing machine. Simply we can say that the alphabet of standard Turing machine either subset or equivalent to the universal Turing machine alphabet. If not, we can. So that fixed alphabet of universal Turing machine is defined with the C, and of course it is not having the blank symbol in the C. Then it will define what you are having the universal Turing machine alphabet, that you have to specify here. So that if you are giving any Turing machine, it will check whether the standard Turing machine alphabet is subset or equivalent to this or not. If not, it can't do it. If so, well and good. Okay. Then how we are going to build a universal Turing machine U for a standard Turing machine? Yes. So simply you have to give the code of the Turing machine, as I told you, and what are the strings you are giving. So if you give this as an input to the universal Turing machine, and it will take all the strings by reaching the final states of your Turing machine. If so, then we can say that it is accepted. Right? So it is nothing but the fixed alphabet union all the universal alphabet. So while you are doing the transition, generally the C won't contain the blank, but you have to add it while you are processing the input string. Okay. So as I told you, it has three steps. Step 1, the contains the code of your standard Turing machine, and step 2 of U same as a single type of S like input string, and step 3 of U contains the current state of the standard Turing machine, your Turing machine, right? So like this. So input type, the codes, and what the Turing machine, standard Turing machine code like description, the input type. Based on the state, this head will move here based on the description and the input symbols. Okay, so what are the steps here? First you have to initialize, so all 0 and square of 0 of tape 3, like whatever the states, and copied the from the standard to the universal Turing machine, and copy the string from tape 1 to tape 2 and return all the 3 8s to the square of 0, right? Then how we have to do it for each step of execution. So again we'll go with that halting state. See, we are saying that both we are having two kinds of acceptance, halting and acceptance. But here generally the universal Turing machine deals with maximum number of times deals with the halting state only. So if it is halt, then we can say that the string is accepted. Whichever is on the tape 1 should be considered as output type. If it is not halting state, you have taken the input string but it is not halting, then what will be happen here? So we can say that the string is not accepted, and if it is not halting means we can say that forcefully we can halt the Turing machine and we can say that the string is not accepted. That is, you moves left repeatedly, you can halt and mention that it is failed, right? So next one, undecidable problems. Guys, if Turing machine is not existed for any problem, right, for any problem, if it is halting or without halting, if Turing machine is possible, we can say that somehow those are decidable languages, right? But if you can't design a Turing machine, then we can say that the problems are undecidable problems. And this, we are having two problems: Turing recognizable languages and Turing decidable languages. See, what is meant by Turing decidable languages? For every string, it should be halted, whether the string is accepting or rejecting, whether it is in the language or not in the language, must be halts. But Turing recognizable, not decidable, we can recognize it with some infinite looping. So it may not halt for some strings which may not be in the language, right? So of course the power of everything is same here. Then undecidability. See, the languages can be decided into recursive enumerable and non-recursive enumerable. These non-recursive enumerable languages are directly undecidable problems. Recursive enumerable languages are semi-decidable. If it is completely recursive, decidable, means no halting problem. If there is a halting problem, but that cannot be converted to acceptance, then we can also say that those problems are undecidable problems, right? So simply unsolvable means, see, undecidable means we have already discussed about the Turing church hypothesis, right? If something cannot be done with the Turing machine, cannot be done with the computer also. The problems which are not even solvable by the computer, those are treated as undecidable problem. You don't need to worry about the Turing machine only. If you feel that, okay, with the computer also we can't solve the problem, that is undecidable. For example, proving a person is good or bad. Even the ChatGPT can't do it, right? Even the robots. We can pretend that someone is good or bad, right? So then we have already discussed decidable properties for the regular languages, DCFL, CFL, right? Then just you can go with the table here. Some problems, membership problem is decidable everywhere, but not in recursive enumerable. Why means for every string it will halt, but here for some strings it may enter into infinite looping. That is, even the membership problem is undecidable means all the remaining all problems are undecidable. In recursive, only the membership problem and the complement of same type are decidable. We can prove that whether it is belongs to that. And the emptiness, completeness, we can't prove. Remaining all, right? So there is no algorithm to prove that the language accepted by the recursive language is empty or finite or something like that. Okay. So in the next video, we will discuss about the Rice theorem.